Okay, today we'll start the reinforcement learning. Start means as a part of introduction. So before this today's class, whatever we have discussed mainly supervised learning and unsupervised learning. In supervised setting, we said that there is a leveled examples are given, and based on level examples, our classifier or our regressor are being trained. At the same of and at the case of unsupervised, there are no level example are not given. Where we have seen that the based on the data distribution, the certain groups, a certain cluster are being formed, and based on these groups, we can somewhat classify or clustering. Now, in this reinforcement learning, uh, things are a bit different. So, how we can say the problems involving an agent? Here, the problem is just involve an agent interacting with an environment. So, this two term is very important here. Rather, I think three term. One is agent, one is environment, where agent is interacting with environment. And these interaction are being evaluated by a numeric signal called reward. Okay. So the thing something like that, there is a prescribed environment where an agent takes some decisions, or more technically takes some actions. An environment is being described by a states of the environment or state of the any you can event. Even maybe a play game, a gameplay or anything. And the action which is being taken by the agent is evaluated by giving a reward. Reward may be positive for making a good move or better move, and maybe negative for a as a penalty. So the what is the goal? Learn how to take actions in order to maximize reward. This is the major goal of the reinforcement learning. Okay. Now here in this diagram, you can see that there is a something agent, this action, reward, next state, and there is some examples of what are games. So one by one, we just try to understand. Okay, let you see this reinforcement learning basically taking two main thing. One is agent who take actions or who take decisions, and another is the environment. Okay, so environment is given by a state at a point of time t. So state st is basically a representation of the environment. Okay, and based on this state s, or better to say, staying at the state s, agent take action a t. A t means at the time instant t. Okay, so please mute yourself. Okay. Now, when action is being this action is being taken, then again the thing is that the this loop or control loop coming to the environment, and based on this action, there the system will generate a reward. Okay, this system is reinforcement learning paradigm or learning system. This RT is going to evaluate the action which is taken, which has been taken as staying at state ST. So this is the basic modeling of the reinforcement learning paradigm. Okay? And when we take action, then we not only we reward this action, but that action will take this agent to the next possible state. Okay, so just take a idea of that, that you just if you take a concept of tic tac toe, you can say. Now tic tac toe is being playing in this way. Now this is the initial state, okay, or zero state, or you can say t0. This is the t0 state, okay. And some just for a player one put a cross mark here. Now when the took a cross mark here, then you see the environment is changed. So action, this is action being taken by, let's say this is a two player of this particular game. So the the action is being, it is t0, this action is being taken, and then it will change. Now initially all the fields are blanks. Now there is a one buttonmarks. So now the question is that what will be your move? So you can move either here, either here, either here, either here, here. So these are the possible position where you can give your dot marks or circle mark. Now question is that where you should give, and what is your goal? Goal to win this game. Okay. Or more pragmatically, you can say not to lose the game. So, okay, so these are given. Now you have in a particular, this is the state, and now you are in a position where to take that, which action you are going to take. Because this is, if you put it, this is action A1 let. So if you put it there, it is A2. If you put it there, it is A3. It is A4, A5, A6, A7, A8. So 8 different action you can take at the state this. And now the question is that which action is being, if you're going to take. Let's say you take this this action. Okay. Now in this way, so now the question is that if you take, if you use this action, then we have to evaluate this action. So this evaluation definitely we have to determine that if you write, put this, what is the probability you are going to win or you are going to draw or you are going to lose. Or if you say any other choice, but and if you are in a more closer to the winning track or winning path, you are being rewarded positively. If you are close to the you can say the draw or losing path, then you are negatively rewarded or something like that. So this is the very in a very nutshell or very simplistically the paradigm of reinforcement learning.
Excuse me, sir.
Yes.
Sir, in the tic-tac-toe example, we were only getting the reward not for every action, only after the whole game is completed, right?
No, no, because whole now what is that in any in these things will basically mean that after game is closed you can say that you win or lose. But if you I if you are if you gone through any AI course or this kind of course, there is some algorithm is there. Now if I said you, this is a very good example or a very but it bit uh, out of context of machine learning. But if you're interested, you can. There any kind of Prolog programming or even Python programming you can. If you want to write a tic-tac-toe game for your own. Now you can see there is a different path. Maybe there is a path of winning, there's a path of drawing, and there's a path of losing. So now the question for a particular, so this is a man versus computer, and you are basically writing the program on behalf of the computer. So it is possible that if you write a program, that this program, when playing with a human, this program never, the human will never win. Okay, so that is possible too. So this path you can choose. So whatever move you are going to do, whatever move the human will going to give, but your move you never lose. Okay, at
Sir,
maximum
I
it
have a
will
doubt.
be there.
Sir,
Yes.
but if I give the agent rewards based on whether the movie played is going to win him the game or not, right? Then doesn't it make this a case of supervised learning? Because we are kind of telling him that okay, this move will win you the game and this move will not win you the
No,
game and all.
no. You are just hold on. Now the thing is that what I'm trying to say. Now this is tic tac toe. Since this is for your understanding, I'm saying. Now if I say, can you write the same program for chess? So what is your problem? So is it problem that if you write a computer program that will play in on behalf of the computer, and that program is not going to lose any time in chess? Can you do that? Can you write a program?
No, sir, not for chess.
Huh? So what is the problem?
But in chess, there are other metrics, right? We can
No,
say
no, no,
that.
no, no. I'm just answer my question. What is the problem you're going to face? The simple, I'm not going a very high thing. Just a very simple understanding. What the problem you will face, and which is not a problem for tic tac toe.
The chess is a very large, like it is
Yes.
exponentially more.
So yes, the number of states and number of action is exponentially high. You cannot maintain within this a kind of your space complexity and time complexity is very high. So that is the problem. Okay, because that's why even a supercomputer cannot do that. You know that there is a one incident, I think the 1880s, first Kasparov is being beaten by a supercomputer, the Deep Blue, if I am not very wrong. That is the first time in IBM is invented that time, the Deep Blue. So what actually they done, they don't know the winning path. They have, so they can calculate to some extent so that they can be. But the
Okay.
situation here is something that, even if you see that a robot is walking, or some robotic device is just going on, and there is some obstacle in front of it. Now what it will do, it will go and just struck it, or it change the move. Okay, I'll say that some example in case of reinforcement learning when we actually discuss it. So the major question here, what you are asking, there is those, you can say that, and in a particular state, we don't know that this is exactly the state which we go, but we at least some stochastic prediction we can do, some sort of probability we can get. So if we go there, the chance factor is this, that much. So that's why it is not fully supervised, you can say, in that
Okay.
way you are thinking. Okay.
Okay. And sir, can you give a small example of a reward here? Just a small example.
No, reward means, look, the reward, the small example reward means, yeah, you can say the I can give you example of a reward. It is basically very much application specific or something like that. That you can say the reward is, here in this tic tac toe example, reward is somewhat um, uh, equals or equally proportional to the winning chance. That you can say that in that way you can give the reward. So this in this move, if just for example, now I'll give you that more. Now there is a now this is the this is the thing. So now if you put it this, the reward is high. If you give this, the reward is high. But if this is a very, let's say it is, if you put this, so your reward is high reward. So let's say 5 hour. So this is a reward. And but if you put this in this position, this in this it is there, or but you mistakenly put it here, then this is the -5 hour, because it will lose. You are going to lose. Understand what is the reward? This is the reward.
Okay, sir.
Okay, fine. Now here another example. This is also just an example that the objective the balance a pole on the top of the movable cart. Okay, so this is, so what is the state? Now first of all, you understand the system. Now here actually this particular cart is something like you can pull it in this way. And when you pull it in general, this particular handle kind of thing, this pole, actually this pole is generally has a tendency to go in this way because of the your just the very normal physics. So now you have to do some sort of force here so that this cart will be in this kind of position idealistically. Okay, so this will be the its position. Okay, so balance a pole on the top of the movable cart, so in this way, so that, so action horizontal force applied on the carts, so how much force you are going to, and reward at one at each time step if the pole is upright. So every time step you are basically, if it is a straight, then you can get one, otherwise zero or minus something. So in this way, if you formalize the reward, then what is the goal? The goal objective of this, what is the objective? I said, learn how to take action in order to maximize the reward. So if you are maximize the reward, in general, your thing is done. Okay. So this is the concept of reinforcement learning. Okay. So this conclude the introduction of our this machine learning course. Now we slowly go to the some detailed discussion. Okay. So we start with supervised learning. Okay. So in supervised learning setup, we know that the examples are being given at the time of the training. So training data comes in a pairs. Now what is the pairs? X and Y, where X belongs to a d-dimensional space, is the input instant, and Y is level. Okay. Just a second. Okay, so what 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 actually we trying to say, that you see that that is the x and y pair. X may be a kind of vector, that is maybe x1, x2, let's say xn. Okay, so this is the n dimensional feature, or you can say feature space. Okay, and that is the another thing, that is y. Okay, if we go through, if we just, if we just recall our example of this apple or not apple example, so that may be this x may be the color, this may be the weight, this may be the, here x3 is maybe the shape, and so on and so forth. Okay, so these are the different feature. And this y, if x is this, then this is say this x, if it is a binary classifier, this say that it is apple or not apple. So this is a only two values, y, 0 and 1. So this is the level. So x is r d, these are basically d-dimensional. Say, let's say it is a d. So it's a d, so d-dimensional feature space and input feature space, and the instance is definitely 2. Okay. Now here what is by x1? Now you can say 1x. Now this is the, this here n is the number of features. So how many such input instant number of, you can now, sorry, number of features, number of instance. So say that number of, so instance means training example. So every training example is a d-dimensional feature space or d-dimensional feature and a corresponding y. So here you can say in this, in here you can see that x1, y1. So x is a d-dimensional, or y is 0 or 1, and up to this xn. This is, so n is the number of instances or the training examples. Okay, so here you can say the same thing, rd the d-dimensional feature space, and this is the feature space. Xi is the input vector of ith sample. So you can say number of training samples, so ith sample. So that's why xi. Xy corresponding y, where y is equal to either 0 or 1, and xi is equal to this. This is, you can say, right, is a kind of vector. Y is the level of the ith sample, C is the level space. Okay, so this is the kind of notation by which we describe this supervised learning setting. Okay, so data points x1, x1, y1 are drawn from some unknown distribution p of xy. Okay, and that is important. One thing is important to understand, that we are taking samples, and we can say we are going to um, train a model, supervised, in supervised paradigm. Model means, you can say, for your sake of sake of simplicity, it is a classifier or regressor. Now the distribution from which we are take this examples, the training examples are known to you, but that doesn't mean you know the distribution. Just for example, if you say that you are taking images of, let's say, dog, for a classifier dog and non-dog classification. Okay, now the question is that the dog images you can take as instance of a this, so a data sample, so some examples you can take, but it may not necessarily say or assume that you know the image distribution. Okay, the total distribution or image distribution you don't know. So the data points x, y, y, x vector, x1 vector and y are drawn from some unknown distribution p of x1, x comma y. Ultimately, we would like to learn a function h such that for a new pair from the likely, from the some sort of similar distribution, so pair xy belongs to P, we have hxy with high probability that hx is equal to y. We will get this letter from now we go to the from example x and y. So what is basically trying, what I'm trying to say, that we are there is a training samples. Let's say xi, this belongs to some sort of distribution P, and now some x, you can say, we can write it xt, that is a testing sample. Let's say this is I that is coming, and this also likely from this distribution, sorry, from this distribution. Okay, then our classifier or hypothesis, this classifier, what is being framed by this you can say this h of x, this is a trained classifier, you can say, that can say that it is, maybe if it is a apple or not apple case, it is apple or not apple. Okay, so this is the basic learning setup. Okay, so now you can say there are multiple scenarios of the level space C, that binary classification, that C is equal to 0 or 1, and generally we use +1 or -1. Okay, so these two things we are generally used. And spam filtering, an email is either spam or not, this kind of is a binary classification. Multi-class classification, you can say that place classification. The person can be exactly one of k identities. Okay. And regression, predict the future temperature of the height of a person. That we can say, that we can say our output space is continuous. Okay. So C is the real. This is a continuous space. And so these are two the discrete space. Okay. Now some more kind of example, some raw images. So now the we try to understand what is the feature space, and that is very important. Now the question is that if you are being given an image, sorry, image or some text or some video, these are your input. So actually what actually is going to, if we do a kind of classification, we are going a very simplistic discussion. So if this is the given, and let's say we are a question of object detection or sentiment analysis or a kind of event detection. I think three classification problem I said, and this object detection from, let's say, from image, text, it is a sentiment classification, and videos is called event detection. So these are the input. Now if I say that without, we don't know anything about machine learning, what is our basic idea, that if this kind of question is being asked, that giving a set of image and say that this is the other particular face is given, and it says, say, okay, let's say this is a person face, or it's animal face, non animal non-human. So that you have to decide what should you do. So this is the, now the question is this: if you think from that point of view, you are going to understand that the what is the actual the research is being learned from last 25 or 30 years, along with the vision engineering or kind of NLP engineering, and use the help of machine learning. What actually we are going to do? Okay, so that is the thing, that if the person is being given, so some this you have to find out some sort of characterization of this raw image, or a text, raw text, or a raw video, so that this characterization is going to help that to understand that this image contains a person's face or an animal's face, or a person in the image or an animal in the image. Okay, so now the question is that, so conventional machine learning, if you say the conventional machine learning, what should we do? What kind of thing we'll do? First of all, we'll do a feature extraction and taking only this object detection, so face image. So the feature extraction means that that when we do the feature extraction, that means what may be the our feature. You recall our apple, this what I said, what will be the feature of an apple? Maybe first of all the weight, then the size, then the color, then the cost, then the shape, and dot dot dot. So these are the characteristics, features, or characteristics of particular fruit called apple. Okay. So the weight is less than, let's say, 50 grams, something like that. I'm saying hypothetically. The size is basically, let's say that particular size, not less than this particular. So cost is, color is maybe red, green, and something like that. Cost is less than, let's say, one apple, what, 20 rupees, or less than 20 rupees. And shape and something, some shape parameters is there. So it's spherical and some sort of, let's say. So these are the characteristics feature which describe a fruit as apple. Okay, so even so, if you are a human face, you are going to understand. Then obviously, what human face is generally, there is some sort of distance between two eyes is not same as the distance between two eyes for a particular horse or a particular cat or something like that, or something, the pattern of that. These are the typical human patterns, some geometrical things, skin color, and so many things. So these are the general feature, that feature we are going to represent. First we're going to extract the feature, and when the feature has been extracted, the feature is basically look like what. Now you see the training data. So these are the different objects it is given. These are all vehicles, and the corresponding training data is that. So ultimate end of the day, that if you say that our feature after feature extraction, these are the total feature, and let's say this is a d-dimensional feature space, d-dimensional feature space, and these features are something this. This is a lot of. I'm not saying we have discussed a lot of things, but this is the kind of, there's a lot of things we have done, feature normalization, all these things. But after that, of all these are the normal features. Okay, so these are the features kind of, and for scale, this is the feature. Let's say 170 is basically kind of color represented. For color, we can normalize such that it's 70. 86 is the color of this. And by for A, this is the color of something like that. I'm not saying exactly. There's some weight parameter also, you can say in that way. Okay. So these things. So these are the, and this vector. So these are the features of what? A dimensional vector. So these d-dimensional vectors are kind of this. So some values. Okay. And there is a label. Label means what? These values denote a bicycle. So it's a label. So these values denote a boat. These values denote a car. These values denote a plane. So our data is now labeled. So this label is being given. Okay, so many, so that it may be the on cycle there is a 50 example of cycles, let's say 25 example of boats, maybe 70 examples of cars, and aeroplane is maybe 25 number of instances aeroplane images being given. Okay, and on based on this we are going to say that the instances of this and corresponding instances. Okay. Now when we can say this feature space is ready, or this feature vector, the feature is ready, then we use this feature to train algorithm. So our ML thing is basically starts here. Okay, so given the, but why I said this kind of, because how you apply ML. So this feature space is very important. But this is very important. Why? It is our input to our machine learning module. So that in this particular class, we are going to understand, given these features, how we are make a classifier. That may be a decision tree, that may be a linear regression, that may be a classification, that may be some kind of anything. If you say classification, there is a different way of doing that. Then the logistic regression you can do, or you can go for a neural net, you can go for support vector machine, and a lot of things there. Deep learning, you can say deep learning. And this algorithm, whatever algorithm you choose, that will going to give a kind of model. That model is a parametric model. That parametric model is going to know that how to differentiate between these classic classes. That is, a bicycle is a class, as a boat is a class, car is a class, aeroplane is a class, and so on. So up to that, that this model is basically ready here. That is trained model. Now how do I have to do? Now we have a test data. Now you see this car is not a part of these instances. This is a new data. That is a card data. It why it is a card data? I'm not giving these are the vehicle. I am not a give a dinosaur. So the I'm giving from a some sort of similar distribution, but not known sample. These samples are not in this particular sample is not used for training, but it is a similar kind of thing. It is not, if you are giving the this here and you can give a kind of you can say elephant, it's not going to work. Okay, so that is the idea actually. So if you say the inference, then your classifier, how accurately you build your classifier, they are going to give it is a kind of car or a bicycle or boat or airplane. Okay, so this is the basic idea of supervised learning, because here these labels are, this is important, that's why the supervised setting, this is being given a priori of our training example, or sorry, the learning, the classifier, or learning the kind of model. Okay, okay, now you can see this input space. Now this is important. Now this particular thing we have now, you definitely, if you say that okay sir, you said that image is being given, and you say there is some values, let's say 100, let's say 72, let's say 35, and just last slide we can say 550 and dot dot dot. How it is possible from image to दे दिया और ये सब कैसे मिल गया? So then that's why the input space is not the feature space. Okay, so these two are different. So that's why I said here that this training data are being given. So this feature extraction part is in between. So image is given, we use some feature extraction. So the diamond, if you say from the dimensional point of view, this is the image. So this input space is somewhat transformed to this feature space. Now, input space, if for the image, it is a 2D image input space. Now, it may not be 2D. You can say the feature space may not be 2D. It's a maybe the D, let's say the K dimensional feature space, okay, or N dimensional feature space. Fine. Now you can see that another important aspect is there. The input space, you can see that sometimes we can give the input space is somewhat in this way. Now you see that this is also a very interesting transformation. So in general, our feature space is something like that. We can get a very easily some sort of we can say distinguishing between two objects. Now just for example, what I'm trying to say, a image of cat is being given and the image of, let's say, dog is being given. Now the question is that in this particular input space, it is very for a classifier, it is very you look these these are the, if this is the represented by in this way, then two images, even these two images means these are the this thing that belongs to cat, and let's say red is belongs to red. Just you superimpose two images, something like that. Just hypothetically assume, because this is a very important concept. That's why I'm coming, because it's one of the very important thing. Now, why this transformation? Why these features is being taken? Okay. Now, also this feature is taken such a way so that this thing can be easily distinguishable. Okay. So that is important, that we can get a feature space, and this feature space is something like that we can do some sort of easily distinguish between these two different class. Now it is not completely end of the story, because maybe possible that you define a feature space, but this feature space you constrain your classifier. No, okay, our classifier is a linear classifier, maybe linear, it may be line, maybe plane, maybe hyperplane, but it's a linear thing. Here, just for example, some assumption is being taken from support vector machine. In general, support vector machine, the hyperplane is a linear hyperplane. So if this is the case, then this feature space, in which particular dimension this linear separability thing will come, that also a question of concern. So I'm not going at the very beginning or this will definitely, these things we are going to understand throughout our course. But just for example, say the input space is not necessarily the feature space. So there is some sort of transformation. Okay. So this is now very interesting. Some sort of bit, some theoretical thing. I just touch upon this. What about the hypothesis class? And there is a one no free lunch theorem. First, you read out what trying to, then I explain what is. Before we can find a function h, we must specify what type of function it is we are looking for. Okay, so the thing is that so what we have at this moment, if you say that we have some given examples, okay, these are the examples, some points is given, and you can say these examples from a particular, which in particular domain there is some example is like this. Let's say supervised setting. Now the question is that how you going to take a distinguish between these two classification. So what will be the what that you can say it is the artificial. So what kind of function you are going to use to separate it out? It may be a linear function, it may be a curve, or maybe anything. Okay. So you can say, so this hypothesis function h, we must specify the type of this function, and that is we looking for. So these functions, these, what are these a hypothesis function? It may be a just simple linear separator. Sometimes also it's a linear regression kind of regression. It may be a support vector machine, that is also linear. It may be a neural net, is a nonlinear. It may be a logistic regression, it is also nonlinear, and so on. So it could be artificial neural network, a decision tree, or many have decision tree. That also be a decision tree. That is also kind of classified. So we call set of possible function as a hypothesis class. Okay. So all possible function, जो जितने सारे possible function हो सकते हैं, उसको हम लोग एक साथ hypothesis class बोलते हैं. So by specifying in hypothesis class, we are encoding important assumption about the type of problem we are trying to learn. So it is also for it's basically application specific for some particular application. So just for example, if it is a continuous output is required, regression, we go for regression. If it's a discrete output, we go for classification and so on, kind of. But what is no lunch theorem? Sorry, no free lunch theorem. It states that every successful machine learning algorithm must make some assumption. Okay. Just what is the assumption? That's just for linear regression. That is a linear, it is the assumption. So our curve is a line if it is a one-dimensional. If it's a two-dimensional, it's a linear plane. Okay. So this linearity is the assumption. So that in the no freelance theorem states that every successful learning must make assumption. This also means that there is no single machine learning algorithm that works for every setting. Okay, and that is very important to understand. It depends on the particular application which we are, and some assumption definitely is there. It is not that एक ऐसा machine learning algorithm आ गया तो सबके लिए चलेगा. This is not possible. So that's why it's a no freelance theorem. Okay, so what we have discussed, I'm summarizing in this supervised, or sometimes we call inductive learning also. So it is the simplest form of learning. F is a target function. We'll see what is f in successive slide. An example pair is x and of f of x. That we are going to understand that x is a training samples, and we trying to find a function f from this x, and given a collection example of f, return a function h that approximate this f. Okay, so that for example, what I'm trying to say, that this is the examples. Okay, so that maybe this is the actual function is this. So what we are basically, for a hypothesis, we may be, if we have a linear function, I am changing the color so you can understand it properly. Now this is the actual function, and but we are basically trying to hypothesize in this function. Okay, so this is our hypothesis, and this is the actual function f. So that there should be, so given a collection of example of f, so and these are collection of these f, these are the examples, these crosses are examples, and based on this we are going to hypothesize this function. Okay, so a hypothesis f, so h is very close to f, actual function, given a training set of examples. Now this f may not be known, because if you know the f, then you know the distribution. So f is not known, but it is basically a kind of imaginary. So this is highly simplified model of real learning. ignores prior knowledge. So prior knowledge F का तो पता नहीं है, but and assume examples are given. So but what we know, the distribution is not known, but you know the examples, some instance of it. So we stop it today. Yeah, we'll discuss. We'll continue discussion of this. So if you have any question, you can ask.